for taking part in the inaugural ceremony of the GIAN course titled Advanced Permanent Magnet Machine Drive Technologies for Transport, Electrification and Renewable Energy under the aegis of Global Initiative of Academic Networks and Initiative of Ministry of Education, Shiksha Mantralaya, Government of India, at NIT Silchar, organized by the Department of Electrical Engineering and scheduled to be held from today, 21st March 2022 to 25th March 2022. For starting the inaugural ceremony proceedings, first of all, I would like to welcome all the distinguished dignitaries present here physically to grace the dais. First, I would like to request the distinguished dignitaries, Professor A.K. Barbier sir, Dean Academic, NIT Silchar, to grace the dais. Sir, Dean Research and Consultancy. Professor Department of Mechanical Engineering, NIT Silchar, and GIAN Local Coordinator. Head of the Department of Electrical Engineering, NIT Silchar. Dr. L.C. Silchar, Associate Professor, Department of Electrical Engineering and the Course Coordinator of the GIAN course. Dr. Sir will be joining shortly. Now, I would like to welcome the distinguished dignitaries present virtually to grace the dais. I request Madam Rukmini Datta, Associate Professor, Energy System Research Group, School of Electrical Engineering and Telecommunications, University of New South Wales, UNSW, Sydney, Australia, and the foreign expert of this GIAN course to grace the dais. Thank you, Madam. Now, on behalf of the Department of Electrical Engineering, NIT Silchar, I, Asha Rani, Assistant Professor, Department of Electrical Engineering, NIT Silchar, welcome you all, and I would like to express my heartfelt gratitude for your presence in this inaugural ceremony of the 5-day GIAN course on Advanced Permanent Magnet Machine Drive Technologies for Transport, Electrification and Renewable Energy, organized by the Department of Electrical Engineering, NIT Silchar. Once again, I would like to extend a warm welcome to all the dignitaries, deans, heads of various departments, faculty members, students, and all the participants present here, both physically and virtually. Now, with the permission of the distinguished dignitaries, we are going to felicitate Advanced Permanent Magnet for Transport, Electrification and Renewable Energy, organized by the Department of Electrical Engineering and Energy. Once again, I would like to extend a warm welcome to all the dignitaries, deans, heads of various departments, faculty members, students, and all the participants present here, both physically and virtually. Now, with the permission of the distinguished dignitaries, we are going to felicitate the guests present physically on the dais. Now I request Dr. Rajiv Desai, Assistant Professor, Department of Electrical Engineering, NIT Silchar, to felicitate Professor A.K. Barbier sir, Dean Academic, NIT Silchar. Now I request Dr. Prashant Roy, Assistant Professor, Department of Electrical Engineering, NIT Silchar, to felicitate Professor S. Vaishya, Dean RNC, NIT Silchar. Thank you, sir. Now I request Dr. Sapna Mansani, Assistant Professor, Department of Electrical Engineering, NIT Silchar, to felicitate Professor P.K. Patwari sir, GIAN Local Coordinator. Thank you, madam. Now I request Dr. Abadpati, Assistant Professor, Department of Electrical Engineering, NIT Silchar, to felicitate Dr. J.P. Mishra, Head of the Department of Electrical Engineering, NIT Silchar. Now I request Dr. Srijit, Assistant Professor, Department of Electrical Engineering, NIT Silchar, to felicitate Dr. L.C. Silchar, Associate Professor of Department of Electrical Engineering and the Course Coordinator of GIAN, Thank you, sir. Now, NIT Silchar on behalf of Department of Electrical Engineering is going to felicitate the dignitary present virtually on the dais. Now, NIT Silchar fraternity is felicitating Dr. Rukmi Datta, Associate Professor, Energy System Research Group, School of Electrical Engineering and Telecommunications, University of New South Wales, UNSW, Sydney, Australia, and the foreign expert of this GIAN course.
Solar line or second filter? Yes. There. Play. Full mode. F5.
Now I request the distinguished dignitaries present here to light the lamp, to bless this morning and the program, invoking the blessings of Goddess Saraswati by kindling the lamp of knowledge, a symbol of brightness, prosperity, and wisdom.
Sir.
Thank you, sir. Now I request Dr. Lalit Chandra Saike, sir, course coordinator of the GIAN course, to deliver the welcome address and to introduce the foreign expert of this GIAN course, Dr. Rukmi Datta, to the participants.
A very good morning to one and all present here. At the same time, good afternoon to Professor Rukmi Datta and Dr. Clay, the postdoctoral scholar of the Rukmi Datta. Honorable Director, NIT Silchar, Professor Shivaji Bandyopadhyay, who will join this inaugural program after a few minutes. Local Coordinator GIAN NIT Silchar, Professor P.K. Pakwari, the SOD Electrical Engineering Department, Dr. J.P. Mishra, the Dean Academic NIT Silchar, Professor A.K. Borbuya, the Dean Research and Consultancy, Professor S. Boiso, the external faculty of the GIAN course, Dr. Rukmi Datta, my faculty colleague, the participants, and the ladies and gentlemen. I hereby welcome all of you to the inaugural ceremony of this GIAN course. We at NIT Silchar delighted to inform you that the GIAN course entitled Advanced Permanent Magnet Machine Drive Technologies for Transport Electrification and Renewable Energy is started today. The application of this particular GIAN course was submitted in October 2019 and finally it was approved in February 2020. The same could not be held due to Corona pandemic. Finally, it is scheduled to held online as per new guidelines. There are 51 participants in this course. Most of them are masters and PhD students from academic institutions of India. A satisfactory number of faculty members from various institutions of India are also registered for this course. We are proud to have you all here, either virtually or physical mode. On this occasion, we are honored to have the Honorable Director, NIT Silchar, Chief Guest of this function, Professor Shivaji Bandyopadhyay, who will join this program after a few minutes. He will deliver the inaugural address and bless the GIAN program. Sir, I extend a very warm welcome to you in advance on behalf of myself and Department of Electrical Engineering and IT Silchar. Professor P.K. Patwari, Professor A.K. Borabhaya, Professor S. Vaishnav are also with us. They will deliver their speech in this inaugural function. I hereby extend my warm welcome to all of you, sir. The person behind this course is the external faculty, Dr. Rukmi Datta, who had accepted my request for this GIAN course in a single mail and had designed this GIAN course. Dr. Rukmi Datta, presently working as an associate professor in Energy System Research Group, School of Electrical Engineering and Telecommunication at University of New South Wales, shortly UNSW, Sydney, Australia. She has received PhD degree from UNSW, Sydney, Australia, and the BE degree from Assam Engineering College, Guwahati, Assam. Dr. Datta is a senior member of IEEE since 2015 and an active member of several IEEE Technical Committee. She is the current Vice Chair of IEEE IAS Electrical Machine Committee. She is also the Regional Distinguished Lecturer of IEEE Region 10. Dr. Datta is an Associate Editor of two prestigious IEEE journals, IEEE Transaction on Industrial Application Society since 2018 and IEEE Transaction on Energy Conversion since 2019. She is also editor and guest editor of several ASIA journals. Her area of research are design of various permanent magnet machines, power electronics converter, electric vehicle, and direct drive wind energy conversion system. I welcome you, Madam. The participants, all the faculty colleagues, the students, and ladies and gentlemen present here, I welcome you to this inaugural function. The primary objective of this GIAN course are, number one, expose participants to the fundamentals of permanent magnet machines and drive technology, building confidence and capability among the participants in industrial adaptation of permanent magnet machine and drive technology, and provide guidance for troubleshooting in design and control of permanent magnet machine drive system. Third one, provide exposure to practical problems and their solutions through case studies in design and control of permanent magnet machines. Enhance the capability of the participants in design and control of permanent magnet machine applicable to emerging technologies. The course is designed for 12 hours lecture class and 8 hours tutorial class. Each of the tutorial class will be followed by MCQ type examination. Though the course is formulated for mainly permanent magnet machines, their design and application. The same is framed in such a way that participants from other disciplines like control, power system, power electronics can easily learn and can be utilized for multidisciplinary research. The secondary objectives. There are many secondary objectives, out of which one is collaboration opportunity. Already NIT Silchar have conducted a meeting on 11 March 2022 with the foreign faculty to explore the collaboration opportunity in terms of students and or faculty exchange, utilization of world-class laboratories, joint PhD guidance and research between University of New South Wales and NIT Silchar. And it was explored that there are mass scopes in this regard, and in future it will be done. We strongly believe that all participants will learn a lot and enjoy this course. With these words, I once again welcome you all. Thank you.
Thank you, sir. All request Dr. J.P. Mishra, sir, Head of the Department of Electrical Engineering and Silchar, to deliver his welcome address.
Very good morning to everyone, as well as very good afternoon to Madam, who is the external staff present over here. It is my great pleasure to deliver welcome address to all dignitaries on the physical as well as virtual dash of this inaugural ceremony of the GIAN course on advanced permanent magnet machine drive technologies for transport, electrification, and renewable energy. Honorable Chief Guest Professor Shivaji Bandyopadhyay, Director NIT Silchar, who has not yet joined, he will join soon for the inaugural address. Honorable Guest and Foreign Expert of GIAN course, Dr. Rukmi Datta, Associate Professor of Energy System Research Group in the School of Electrical Engineering and Telecommunications at University of New South Wales, Sydney, Australia. Respected Dean Academic, NIT Silchar, Professor A.K. Maruya. Respected Dean Research and Consultancy, NIT Silchar, Professor S. Bashir. Respected Local GIAN Coordinator of NIT Silchar, Professor P.K. Patwari. Dr. L.C. Saikia, the Coordinator of GIAN course, as well as Dr. Clay Chu, who is the PhD scholar of the New South Wales, Sydney, Australia. He has also joined this inaugural session. Esteemed faculty colleagues, dear participants from academia, industry, and research laboratory all across India. On behalf of Department of Electrical Engineering, NIT Silchar, would like to extend my warm welcome to all the dignitaries and participants in this inaugural function of GIAN course on advanced permanent magnet machine drive technologies for transport, electrification, and renewable energy, organized by the Department of Electrical Engineering, NIT Silchar, under the initiative of Ministry of Education, Government of India. I thank you all for joining this inaugural function. The theme of this course is focused on industrial motor drive systems, its improved performance and efficiency, mainly the application of permanent magnet machine in the newly proposed transport, electrification, and renewable energy systems for the sustainable development. The course is expected to provide full comprehensive knowledge about permanent magnet machines and drive technology, which will be highly beneficial for all the participants to understand the fundamentals of permanent magnet machines and drive systems, as it is the future technology of the choice. This course, as cited by Dr. Silchar, the coordinator of the course, is mainly designed to address the fundamentals of permanent magnet machines and drive technology, industrial adoption and troubleshooting in the design and control of permanent machines drive systems, practical problems and their solutions through case studies in design and control of permanent magnet machines and design and control of permanent magnet machines applicable to emerging technology like transport, electrification and renewable energy systems. As a part of this GIAN course, the Department of Electrical Engineering and Silchar had already initiated a discussion meeting on 11th March of 2022 on various collaboration opportunities with the foreign faculty expert, Dr. Rukmi Datta. However, it is expected more intensive discussions between the participants and the external expert during the collaboration of the GIAN course itself. I thank our foreign expert, Dr. Rukmi Datta, for joining this inaugural function, as well as for accepting our invitation for delivering talks with her intense expertise to make this program more interesting and informative. This GIAN course would provide unique opportunities and platform for the participants from academia and industry to have exposure on new developments and advances in permanent magnet machines and drive technology to develop the new ideas and avenues for doing any collaborative research work in the newly proposed transport, electrification and renewable energy field of applications for sustainable development through the initiative of conducting different possible faculty and student exchange programs. My best wishes to the coordinator, Dr. Silchar, and his team members for a grand success of this GIAN course. Thank you.
Thank you, sir. Now, our honorable director, sir, Silchar, Professor Shivati sir, and the chief guest of today's inaugural ceremony has joined us. Welcome, sir. Now, I request Professor B.K. sir, Professor Department of Electrical Engineering and Silchar, to facilitate our honorable director, sir, and the chief guest of today's inaugural ceremony. Now, I request our honorable director, sir, to deliver the notice to the members.
A very good morning to our GIAN speaker from Australia, the daughter of the son of Assam, Dr. Rukmi Datta, my colleagues at NIT Silchar, the dear participants, which includes faculties and the would-be faculties as well, because the GIAN program is supposed to foster the collaboration between two institutions and obviously on some theme topics. In today's world, we focus on research and innovation, and so that the normal teaching learning process activities, so we extend that to the teaching learning and the research activities as well. So it is not that the PhD or the master students they basically carry out research, the undergraduate students also. They are to be endowed with the research culture so that they can contribute for the future development of the society. Now, the growth of the society obviously depends on the usage of the electrical energy, because the devices have to be run, the industry, the drives will have to work on, and for that we require electrical machines. But when we talk about the development, so we'll have to talk about the sustainability issues as well. One is obviously that energy is not limited, but at the same time, the climate change issues also come into picture. Now, when you talk about electrical machines, the permanent magnet machine, electrical machines or the PM machines, they basically have the high level of reliability and as well as the effect. And these permanent machines, the different drives that they are running with specific focus on transport electrification and the drives for the renewable energy. Electric vehicles, then all electric aircrafts, so on and so forth. So this area, that is the focus point of this GIAN program, is the advanced pharma PM machine, the drive technologies for the transport electrification and renewable energy. And NIT Silchar also in our pursuit for keep playing a major role in the development of the society and the mankind. We are putting our focus on the renewable energy aspect as well, and as well as on the transport area at that same time. Just today in the morning, we opened up a innovation workshop on sustainability and entrepreneurship in transportation engineering. Later on, we have innovation programs also in the area of renewable energy, biodiesel, and among other things. So the institute as a whole is geared towards that. And just a few days ago, we had a brief introductory meeting with Dr. Dotto also regarding how the collaborations between the two institutions can progress. And I think today's meet, that is the program that we are starting today, GIAN program. So that initiates the path of the journey. And already, that is when we have an approved GIAN project, so that obviously signifies that collaborations are there. That is continuing, and we understand that in the future, most such opportunities will come up, as we understand that have been taken care of in the last interaction meetings with Dr. Dotto and with participants from NIT Silchar also. With this, and wishing that the GIAN program will not only be limited itself to a single program, but it will foster towards permanent collaborative activities between the two institutes, faculty level as well as at the student level, and that ranges from PhD masters to the undergraduate students as well. With these wishes, I wish the program, GIAN program, a grand success. So the participants will be there. So you interact with Dr. Dotto, and so that more and more collaborative situations can come up, more and more research activities you can take up for the future of the society. Thank you.
Thank you, sir, for your kind and motivational words and for enlightening the participants with your words of wisdom. Now, I request Professor Vigil, Professor, Department of Mechanical Engineering and GIAN Program Coordinator to deliver.
Thank you, Dr. A very good morning to all present here in this inauguration ceremony of the GIAN course. Respected Director, Professor Shivaji Bandyopadhyay, Dean Academic, Professor A.K. Barmiya, Professor S. Bosio, Dean RC, Professor J.P. Mishra, the HOD in the Department of Electrical Engineering, the course coordinator, Professor L.C. Silchar, all the professors present here, and the student participants. I, as a local coordinator of GIAN program at NIT Silchar, welcome all of you to this course that is on permanent magnet machine drive technologies. I express my sincere thanks to Ministry of Education, Shiksha Mantralaya, and the National Coordinator IIT Kharagpur for giving us the opportunity to have this course in our institute. So we are very much thankful to them. And I must congratulate the Department of Electrical Engineering for getting this opportunity and bringing this course in the institute and and the department. So I would like to congratulate Professor Silchar for the effort he has given, and this course is going to be realized from today. NIT Silchar has conducted already 17 courses in phase 1 and phase 2. And I feel very happy to share with you that. So it's a very good number we have achieved. And in this third phase, we have already a number of courses in the pipeline. And this course is the 18th course. And after this corona pandemic period, this is the first course is being conducted in the institute. So I am very much excited to have these courses in the institute. And I believe that in near future, we will have more and more number of courses so that we get these opportunities for this interaction. As you know that the GIAN course is not only for conducting a 40 hours class or 20 hours classes and teaching the courses only. In addition to that, one of the main purpose of this GIAN course is to build a network. And in this regard, I am very much thankful to Dr. Rukmi Datta, the foreign faculty expert, for accepting our invitation and to be with us in this GIAN course. And I believe that the multiple dimensions of the GIAN course will be realized by the support of Dr. Rukmi Datta. I welcome you, madam, in this course, and we are very much excited to have you in this program. And would have been more exciting moment for us that if you would have been in the campus. But even though you are out of the campus, you are away from us, but still you are very close to us. And with this, I do not want to share many other things. I do not want to talk right now. So I wish all the success to this course. And appeal to the participant, please don't miss a single class and be interactive and try to have the best opportunities out of this course. Thank you. Thanks a lot.
Thank you, sir, for the comments. Now I request Professor A.K. Prabhuya, sir, Dean Academic and Education.
Good morning, respected director, Professor Shivaju Pandavardhan, our expert of the foreign expert for this program, Dr. Rukmi Datta, Professor Sumanta Bosho, Dean RNC, Professor Patwari, P.K. Patwari, Global Coordinator of GIAN COURSE, Development Department, Dr. Jackie Miso, Coordinator of this program, Dr. L.C. Silchar, faculty members, dear participants. First of all, I am very happy that NIT Silchar is regularly organizing various co-curricular activities or programs like GIAN COURSE, activity program, seminar, workshops. So as our director sir has already pointed out that today 4 courses are going to start. These types of co-curricular activities programs, one by the civil engineering department, this is by electrical, another one is also by electrical engineering department, and in the afternoon another by Department of Management Studies. So these show our involvement or improvement, I can say, from last few years. Idea we used to organize one or two programs in a month. Now today, in a single day, we are organizing or celebrating 4 programs. So I am happy that this program will be a successful one, and it will help the participants to get an understanding regarding the advancement in the field of permanent magnet machine drive technologies for transport electrification and renewable energy. So what I understand is that the demand of electrical energy is directly related to the demand of or the pace of our development. With the development, the demand for electrical energy is increasing. And at the same time, considering the environmental aspect, the use of other source of energy like petroleum, other gases, we have to reduce. So now the thing is that there is also limitation. We cannot generate electrical energy. This is also nowadays electrical energy, hydropower, from hydropower, thermal, and from wind, other sources. So to improve the efficiency of the machines. Nowadays, in all aspects, not only electrical engineering, other branch of engineering, we have to improve the efficiency. So I am sure that this course will analyze or highlight the efficiencies, how the permanent magnet machine drive can improve the efficiency. And I am sure our participants will be benefited, and other aspects as already our coordinator, local coordinator, Professor Peter Padore and others have also pointed out. It will give an opportunity to establish a network with other institutes, and I am sure with the delegation of Dr. Rukmi Dutta, it will enhance. And with these few words, I wish this GIAN program against success. Thank you.
Thank you, sir, for your kind words. Now I request Professor Silchar, Dean RNC and Silchar, to deliver his address.
के लिए तो चीज भी जाए ना अच्छा लगता है Alok, please mute yourself.
Very good evening to all. Expert, police, electrical engineering, Dr. Cynthia, other colleagues on the layers, participants, and students. In the recent years, we have been conducting such courses regularly. But compared to 2 or 3 years ago, if I see today's courses, more research oriented. This is really encouraging, It means we already achieved our level, acceptable level in teaching, and we are focusing now on research. This is very much encouraging. And today's course, which the two key words, transport electrification and renewable energy, both are very relevant for today's demand of the society. And research in this area shall definitely be useful for the sustained progress of science. This will definitely be useful to the society. And as our local coordinator has that this is the first course of pending study. So I congratulate for organizing such a wonderful course. Another thing which I didn't realize, and I have seen that all the GIAN courses basically have two major objectives. One is the teaching the GIAN topic, and as our director sir has already pointed out, network is already there. So I think before starting the course, 50% successful result. So this is a congratulation to the department as well as to the coordinator. So after attending this country's deliberations from the expert, our participants will learn a lot and they will be able to contribute research in this area, which will definitely be useful for their personal career as well as to enhance the visibility of this institute. Another design of this course will definitely be useful for quizzes. So quizzes will definitely be useful in the sense that will force the learners to learn, not just to attend the classes. So I wish successful end of this course and all the best to the course coordinator and in particular to the participants. Thank you.
Thank you, sir, for your kind introduction words. Now, I request Dr. Gupta Madam, Associate Professor, Energy System Research Group, School of Electrical Engineering and Telecommunications, University of New South Wales, USW Sydney, Australia, and the foreign expert of this GIAN course to deliver her remainder address.
Can you hear me? Good morning.
Yes, madam, you're audible.
Thank you very much. Can I share a screen? Because I thought I will just show you some of the things about our university to make you acquaintance with UNSW. So I'm going to share a screen and hopefully you will be able to see it. Let me know. Could you see it?
Yes, madam.
Okay, thank you very much, first of all, to all of you to be present here to inaugurate this course. I also thank with my heart that GIAN has given us this opportunity to start something which could be very important for both of these two institutes, NIT Silchar as well as UNSW. And I am really grateful to be having this collaboration with a premium institute like NIT Silchar. I still fondly recall when I was doing my bachelor's degree, and at that time NIT Silchar was REC Silchar, and we used to have question paper either from our university, Assam Engineering College, or from Silchar. And then whenever it comes from Silchar, we are all used to be very scared because it will come out of our syllabus or something. But even at that time, the high standard was always maintained in REC Silchar, which is now NIT Silchar. How does this collaboration begin? It's kind of a story to be told, I guess. I received an email from Lalit, Dr. Silchar. I didn't know him at that time, and I was kind of a little bit surprised to receive the email. However, I was aware of GIAN program because some years ago, IIT Kharagpur actually approached us for a similar type of a course. However, at that time, it didn't happen. So when Dr. Silchar reached out to me, I was very glad that I thought maybe we can do something together and could provide a course through the GIAN program. I still remember replying back to Lalit from airport. I was traveling to US at that time to attend a conference, and I saw the email and I replied from the airport saying that I'll be interested. And that's how it began. We start talking about how to proceed, and then we submitted the application in 2019, which was successful in 2020. However, due to COVID, obviously we couldn't do it, or I couldn't come to Silchar to present it at that time. And we waited nearly 2 years now and decided to go ahead as online. So that's why we are here now to introduce you to UNSW. So let me talk a little bit about Australia. We are like nearly 7,000 kilometers away yourself, India and Australia. And it is the marvel of technology that we are get connected. Even though COVID was such a bad thing, but it has also something positive come out of it. That was this technology that now delivering lecture online is kind of normal, and it is so easy. I think this is something good which has come out of it. In Australia, Sydney is one of the major metropolitan city. It's a multicultural city, a city of 5.3 million population, so quite large in world standard, and it's very beautiful. Australia is well known for, perhaps many of you know, the unique animals, kangaroo, koala, but then it's also known for its beautiful beaches and World Heritage Area, the Great Barrier Reef, which many of you might have seen in the movie that Finding Nemo, a little children's movie. And it's really as beautiful as that animation. Then in the middle of Australia sits the big desert. It's a red earth, kind of, and it is even compared with the red planet Mars. It looks even some of the experiment that was previously performed in Australian desert before the exploration to red planet Mars. So it seems to be very close to red planet, that part of the Australia. Now in Australia, there are quite a number of large universities. Out of them, one is University in New South Wales, or UNSW in short form. We are located in Sydney, one campus, and another one is in Canberra, which is the capital of Australia. We are ranked 43 in QS ranking, world ranking, and it consists of many different faculties, not just engineering. So that's why we have a student number such as 60,000. Out of that, there are nearly 25,000 international students from 137 countries. So it's kind of a global university, as you can see. top 10 countries from which the international student comes includes China, Hong Kong, Malaysia, Indonesia, Singapore, Korea, US, and of course, India, Vietnam, and Thailand. So it is, in true sense, a global university. You can find all kind of culture, not just in Sydney, but also in our own university. We always feels at home because it feels like we people from all different part of the world coming together to do something in collaboration. Is there a question? I saw a hand raised. Mukesh Kumar, do you have a question? Hello? Is there a question? Do you have a question, Mukesh?
Ma'am, can you hear us?
No, madam, please go ahead, madam.
Okay, all right. Okay, so in UNSW, actually UNSW is well known for its engineering faculty, although it has law, medical, and humanities as well. And engineering faculty is again largest in Australia. We have in engineering faculty itself nearly 17,000 students, and faculties consist of 8 schools. We call not department, we call schools because each school has their own buildings, kind of, so it doesn't feel like department. We have from biomedical to photovoltaic renewable engineering schools. Of course, traditional civil, mechanical, electricals there. And all of these schools are actually in top 10 in the QS subject ranking. And all of us are actually number 1 in Australia in all these schools. You can see a few nice buildings that has actually recently been constructed in our campus. This is science building, engineering and science. Here is the mechanical engineering school, actually, Ainsworth building. This is another new building. And you can see a few students' facilities or lab facilities here. This is for undergraduate student. This is our actually quantum engineering lab. UNSW, our School of Electrical Engineering, is one of the pioneer in quantum computer building. So this is one of that facility there. Oh, this is another facility. Then coming to School of Electrical Engineering, we consist of 5 research groups, out of which energy system, which I belong to. And we offer not just electrical engineering as specialization, we also offer telecommunication engineering as a specialization, quantum engineering, and also space and aerospace engineering. We have about 2,000 students in electrical engineering, which consist of not just undergraduate, but postgraduate and PhD included. Professor, we have about 20 professors and 7 associate professors and 8 and 10 lecturers, senior and lecturers. And then we have a quite large number of technical staffs who are like our main like support for running the labs and lab facilities. So you can again see a few pictures of electrical engineering labs here. One is here, what you can see this for telecom. It's a like where sound can be filtered very, I think, aggressively. Then you can also see the top our high voltage engineering lab is one of the unique, and it seems to be one and only in Southern Hemisphere. We could have access up to 230 kV or 250 kV high voltage. Also, we have real-time digital simulation systems. These can be used for doing microgrid research, grid forming power electronics, converter research, also many other high voltage DC, HVDC research, multi-level converter research. All those can be simulated and tested in these RTDS systems. There you can see again some facilities for student lab. Now, under electrical engineering, as I said, I belong to Energy System Research Group. So under Energy System Research Group, starting from renewable energy to energy economics, we have all the area that's covered by energy system. Most of us, like we have 3 professors, 3 associate professors, and a couple of lecturers and senior lecturers, then several postdoctoral research fellow and PhD students. All of us are involved in many of these research areas. Some of us are more specialized in certain areas, but we are all actually involved in quite a lot of other or we do quite a lot of good collaboration among our colleagues. So we do work mostly in all of these areas. Obviously, energy economics could be more specialized for someone, and similarly, like for me, the electric machines, drives, and power electronics is more specialized to me compared to obviously energy economy. So I'm going to show you a few slides related to our research that's especially in my area. So we were involved in designing permanent magnet machines for quite a long time now, since 2000, maybe even earlier than that. Now, about 1998 around, I think the first machine that you can see was about that time. And then I got involved in this research through my PhD program in 2002. And the second machine that you are seeing here, that at the top slide, top picture, that is the first one I got involved. And then since then, all the other machines that you have seen I was involved in all those projects, and some of them actually got patented. So were considered for commercialization. We have also developed a number of machine optimization programs based on like AI-driven techniques, including genetic algorithm. So we maybe talk about a little bit of those things during the course. You can also see some other facilities. So we do have emulator systems for a wind energy conversion. At the top second picture, the first picture is for again a wide speed range motor drive system, which can be used to emulate electric traction drives. We have many of them. In the bottom picture you can see, but one is just zoomed up at the top. And most of this drive obviously includes not just the motor and its load, but also its controllers. Most of the time we use our control or develop our controls using National Instruments Microlab box or D-Space boards. And then we of course have other things like the transformers, variac, inverter, power analyzer, whatever is required for measuring and verifying our research hypothesis or theories. We also have developed other type of motors. That's one you can see is a very thin pancake type. Other one, the bottom one, you can see it's actually a multi-phase electric machine with 5 phases. We do have drive systems for this type of special machines as well. You can see a few other power electronics inverters here, one with 5-phase 2-level inverter, 3-phase 2-level inverters are pretty common in our lab. Current sensors, boards, control dispatch control board, they are again quite standard and can be found in all our experimental setup to which our students, PhD students, and sometimes also master students are involved. We also have, in fact, a silicon carbide inverter, which we have built recently as we developed a very high-speed electric machine, only very recent times. And for this type of high-speed machines requires very high frequency inverters. And because of that, we have built this silicon carbide inverter in-house. So many of the things we actually, not just we do the research, but we build and test in-house. So that's the fun part of the research in our university. It's not just like theory, it's always learning by doing things in hands, with hands. And that is also the motto of UNSW, engineering especially. So these are some facilities which are available if we do collaboration. For some of you, if you come here for short stay or would like to explore higher study, etc., which I hope some will be able to achieve someday. There are opportunities, most likely through Australia and India strategic research grants are there, so maybe those can be explored. Although getting a scholarship at UNSW is not easy, I will not say it's an easy task. It's a very competitive affair, as the international students has to compete against like all over the world people come. So it's a quite highly competitive case. But of course, for others like postdoc or even for faculty exchange, there could be some India, Australia strategic grants. I think there are a few which could be explored if someone wants to come and do some short stay and do some research with us. And you will always be welcome. And I hope from this course, that sort of collaboration will happen. And maybe later it could expand to the institute level. That's what my hope. Thank you very much.
Thank you for being present here with us for the enabling ceremony and for your inspiring words. And also for sharing with us a few beautiful views of Australia and the Institute UNSW and the facilities and new research areas of the Department of Engineering UNSW. And also for sharing with us the possible collaboration opportunities with energy Silchar. Thank you so much, ma'am. Definitely we will explore this. Now I would like to request Dr. S.C. Silchar, sir, Associate Professor, Department of Electrical Engineering and Silchar, and the course coordinator of the GIAN course to deliver the overview.
Director, Energy Silchar, Professor Dr. Expert, Dr. Our news is on the dais, the participants, my colleagues, ladies and gentlemen. It is my privilege to have been asked to propose a group of things from this event. I, on behalf of Electrical Engineering Department and the entire MIT Silchar, offer hearty thanks to all of you. First of all, I am thankful to Almighty to giving us this courage to start this GIAN course. I extend my hearty group of thanks to Professor Siddharthi Bandhu for his and time which encourages us towards the fulfillment of this particular function. I also like to thank our director sir for your all support to organize this GIAN course. Dr. Rupi Doctor, the foreign expert, has given us time and encouraged us to make this inaugural ceremony a great success. I extend my hearty vote of thanks to you, madam. I would like to offer my vote of thanks to Professor P.K. Patwari, the local GIAN coordinator, who have graced us with his words. I must mention our deep sense of appreciation to Professor A.K. Bordia, Professor Simanto Bisso, for their valuable skills and time given for this function. Thank you, sir. I would like to offer a vote of thanks to all the professors of my department, my colleagues of the Electrical Engineering Department, for their presence and valuable advice to make this ceremony a great success. I extend my vote of thanks to Dr. Naresh Babu, CSE Department and MIT Silchar, who is working hard for this last 2 days to make this program success. Without participants, it is not possible to conduct this GIAN course and this inaugural function. I extend my vote of thanks to all of you. I would like to thank all the entire PhD students of Electrical Engineering Department, MIT Silchar, to help us to conduct this inaugural function. At last, I extend my vote of thanks to all the students, faculty members of MIT Silchar, and ladies and gentlemen present here in this inaugural function. With these words, I conclude my vote of thanks. Thank you.
Thank you, sir. Now we have come to the closure of the annual ceremony of this GIAN course titled Advanced Thermal and Electrical Technologies for Transport, Electrification and Renewable Energy, organizing by the Department of Electrical Engineering and Energy Silchar from today, 21st March 2022 to 25th March 2022. Hope these 5 days will enable the participants with new and fruitful research path. Now we request our Honorable Director sir to declare the principal secretary.
I declare the GIAN program on advanced permanent magnetic machine, drive technologies for transport, electrification, and renewable energy open. Thank you.
Thank you, sir. Once again, thank you all for joining us in this annual ceremony. Have a good day. So, requesting the dignitaries, faculty members, and all the participants gathered here to join the high tea arranged outside. And for the participants, there will be 15 minutes break now. After that, the session will start. Thank you, madam. So, we'll join and see you during the session.
Compulsory uncontained project routine. అదే ఉంది కదా నేను వెబ్సైట్ ఓపెన్ చేశాను అది ఓపెన్ చేశాను
Actually, there is no need to log in. The top platform. He is going to be only the profile. Nothing more. If you open that word file there,
like my maths we have done right. And this is but
I say then I'll go for class.
okay.
One class over trying to take. Second very
then I
अगर वो ज्वाइन कर रहा है इसका यदि ऑडियो बंद नहीं करेंगे तो प्रॉब्लम होता है।
Okay, so we can continue up to 3:30, no problem. Okay. Then after that, we will start with 1:30.
ওইটা তো এরারে আর বারবার পরীক্ষা দিয়ে এরারে বুঝে কেন এর ওই কোনো রকম আছে তো তার সাথে একটা করে দিকে সব লিখতে এটা ওপেন অফার একটু বুঝতে পারবে এবং যে প্রত্যেকবার ওপেন मजबूरी से पूरा बेस्ट मुझे आगे की चिंता करना जो आपका मैकेनिकल कुछ आदिमल के एरा तो कारण इसका स्टूडेंट का बुझते पारे स्टूडेंट को बुझते समझे नहीं मैं इलेक्ट्रिक और गाड़ी सारे गाड़ी क्यों ना वो गाड़ी का मैं क्या क्लियर कर class
Please come forward and occupy the screen.
After that, there will be no problem. These two sessions only. These two sessions last day 2 hours. Last 2 hours. इसी दिया है मत काम So now we can start now.
Hello. Yes, I'm here.
Shall we start this lecture?
Yeah, or everyone, if everyone's ready, yes, we can.
Okay, ma'am. Thank you, ma'am. Yeah, a very good morning all and good afternoon, Dr. Ratana. A warm welcome to all for the GIAN course entitled Advanced Permanent Magnet Machine Drive Technologies for Transport, Electrification and Renewable Energy. Today we have Dr. Rukmi Datta, Associate Professor from UNSW Sydney, to deliver a lecture on Introduction to EV Drives and Renewable Energy Conversion Challenges. I welcome you, ma'am. It's my pleasure to give a brief introduction of Dr. Datta, ma'am. Dr. Rukmi Datta, presently working as an Associate Professor in the Energy System Research Group, School of Electrical Engineering and Telecommunications at the University of New South Wales, UNSW Sydney, Australia. She had received a PhD degree in Electrical Engineering from UNSW Sydney, Australia in 2007 and a BA degree in Electrical Engineering from Assam Engineering College, Guwahati University, Assam, India in 1996. Before the present position, Associate Professor Datta worked as an electrical engineer at CNG Private Limited and as an associate lecturer at UNSW Australia. She also worked briefly as a research assistant at the Institute of Industrial Science of Tokyo University, Japan, and as an electrical engineer at Reliance Industry Limited, India. Dr. Datta is a senior member of IEEE since 2015 and an active member of several IEEE technical committees. She is the current vice chair of the IEEE IAS Electric Machine Committee. She is also the regional distinguished lecturer of IEEE Region 10. She is an associate editor of 2 prestigious IEEE journals, IEEE Transactions on Industrial Application Society from 2018 to till now and IEEE Transactions on Energy Conversions 2019 to present. She is also a guest editor of Elsewhere's Renewable and Sustainable Energy Reviews. She has served as an editor of several other technical journals, including the special issue of MDPI's Energies. Dr. Datta's overall research output comprises of 1 scholarly book, 3 book chapters, 30 Scoopers Index journal articles, and 91 Scoopers Index conference articles with 1,420 citations and a H-index of 21 Google Scholar 2020-22. She has attracted over 10 million Australian dollars for her research from the Australian Research Council's Discovery Projects, Australian Government Industry Connection Funds, and various competitive research grants. She is currently supervising 6 PhDs, 1 postdoctoral fellow, and in the past supervise 50 PhDs and 3 MPhil students. It's our privilege to have you, ma'am, with us today. Once again, welcome, ma'am, for GAN workshop. Thank you, and over to you, ma'am.
Thank you very much. Welcome to GIAN course. I hope you will get something out of this course. I'm going to share my screen now. Could you see it?
Yes, ma'am. Yeah, you see it.
Okay, and let me just turn on a laser pointer so that I can point to things. Now, the way we would like to run the course is that usually I will present my content, but if you have questions, you can always stop me in between, or you can hold to your question till we finish part of the kind of a section of the lectures. So it will be kind of in 30 to 40 minute sections, and after these sections, we could have the question answers, or you can stop me in between, whichever you think will work for you. Okay, you can raise hand in the Zoom if you are joining as online participant, and I can see if you raise hand, then I will know if you have questions. And those who are in the class and would like to ask question, maybe hopefully I will be able to see, or not if someone could alert me. So again, welcome to this course. It is, as you have hearing this all morning, that it's about permanent magnet machine drive technology for transport electrification and renewable energy conversion. We will have this course for next 4-5 days, starting today. Today is first part is an introduction, that is the morning half, and since all of you are not from the same background, so we thought that having a refresher on electromagnetics will be useful, since we'll be talking a lot about machine design, machine model, and all this involve actually electromagnetics. And if you are not involved in the electric machine drive research, we may not remember some of the even fundamentals of electromagnetics. But without those, it could be very difficult, or some may find it difficult to understand. That's why we decided to have this refresher course in the second half of today, and that will be run by Dr. Silchar. After the course, there will be a short quiz, very easy. Do not at all stress about the quiz. In the quiz, it is actually online quiz. So once you select the answer, and it will come to us, and it will be automatically, in fact, you will be graded. And there will be quizzes at the end of each day, so that at the end of the course, you can get a grade for the course, as it will be, which you will be able to probably provide in your CV or resume. So first part, as I said, is introduction. Second, they actually will start looking at more closely at the permanent magnet machines, which will continue in the third day. So first, and then you will also learn how to design this type of machine using software such as finite element analysis during the tutorials, so hands-on. We know how the software, accessing the software could be difficult, but there are some free softwares which could be downloaded and could be tried off. So that's one option. Then the fourth day, we will be looking at the control of the permanent magnet machines. So usually control can be investigated or understand using MATLAB Simulink. My understanding is that many of you know MATLAB Simulink or have used MATLAB Simulink, but in the course you will learn how to build a control, field-oriented control for permanent magnet machine. Again, during the lecture, you will learn the theory, and then during the tutorial, you will build such a control in using MATLAB Simulink. And I am hoping that you will have access to the MATLAB Simulink for that fourth day tutorial. The last day, we will be looking at a more advanced, that is design and performance of permanent magnet machines, which is again involves finite element analysis. And then in the tutorial, you may at least you will have a demonstration how this works. And I hope that especially those who are interested to explore research in this area, the course will help you to build the fundamental. And that last day, I understand there's going to be also a valedictory ceremony at the end, so in which you will be able to get your grade and a certificate. Dr. Silchar will probably elaborate a bit more in the second half of today's lecture before he begins about that process. In the quiz, actually, we will be asking your name and your application number as the first two questions so that we know who is answering the questions. Otherwise, it will be difficult for us to grade you. So that's why please definitely enter your name and your number in the quiz first two questions. Okay. Is there any questions here from anyone? For me? Himanshu, yes? You can also use chat if your mic is not working or anything. Okay, so yes, Manju, I can see your chat. So you can type your question or you can ask by turning on your mic. So you cannot, in this course, Himanshu is asking whether he can learn RTDS Hill. You cannot learn RTDS Hill in this course, unfortunately, because that's not part of it. But you will see where Hill can be applied. That is where RTDS can come in. So you will see the points, but we will not be going. You will not be able to do that, okay? Unfortunately, because this course was developed more using Simulink and finite element analysis rather than RTDS or Hill. In fact, I have to say that although Hill is good, but it is not as good as precise actually compared to finite element model. Hill is good if you are developing converters or inverters, Nobel converter or inverters, but it's not enough or sufficient if you are designing new motors, okay? Yeah, maybe in future course. Okay, so. So let's start then for today's. The first section, as I said, 30 to 45 minutes based on how we go. What are the two learning goals for this first section is that you will understand the importance of traction drive, and you will be able to list out what are the desirable performance of an electric motor for a traction drive. So the first question is, why do we want to do a electric our transports? And we have to look at the few very sombering effects that's coming up in recent times. One is, of course, the annual temperature rise of the our one and only planet Earth. And we would like to reduce or stabilize this temperature increase to 1.5 degrees C. But to do that, we have to reduce, obviously, CO2 emission. And where the CO2 emission or greenhouse gas is coming from, if you look at in your left-hand side picture, you can see that majority actually comes from energy sector. And under energy sector, one of the key contributor is the transport. And of course, other one is the heavy industries. Now, both heavy industry or transport actually the users of electric motors. So we have a big part to play, especially those who are involved in electric motor and drives in reducing greenhouse gases. Now, what are the targets? So according to US research, what they want to do is reduce the carbon dioxide or CO2 emission by 2026, not very far off, to 163 gram per mile. Whereas European Union wants it to reduce to 130 gram per kilometer. And my understanding is long-term goal for India is to not to exceed per capita emission of the developed world. So all this, like including India, need to play a part here to reduce CO2 emission. So how can you do that? In case of, obviously, for transport electrification, we'll be using electric vehicles. And other one is renewable energy sector. We can look at the global investment trend here, and which tells us where the future research money going to be, in fact. And you can see that the electrified transport, along with renewable energy, the fund, the research investments growing since last 2 decades, and it is expected to grow even more for next 3 decades. So why do we need this investment is obviously to the system that we have is not sufficient. We have to improve on it. And some solution, as I have mentioned, transport electrification. So what do we mean by transport electrification? One is that you are not going to use fossil fuel anymore. We are not going to use the engines, IC engines, instead of all these transports. All these vehicles will be run by electrical energy. And how does electrical energy can do that? It's actually a motor, electric motor. And the other side of the picture is that we are going to have, as the renewable energy penetrates more and more to the grid, the standard grid, it's going to be more decentralized, or it will be localized. So in the localized grid, which is the microgrid, which is quite popular in energy research, we look at the system. Very often we do a lot of research on system integration, system stability in terms when we do research on microgrid. But we often forget that all this in the microgrid, actually, for most of the devices that are in the microgrid, including your generator, wind generator, or even in future, there are going to be probably hydrogen, fuel cell driven generators. Or if you look at the main consumers of energy, it could be your elevator, it could be the air conditioning system, it could be your EV in future. But in all these, actually, under there is an electric machine. And how stable your system is doesn't matter until you have this that electric machine, efficient electric machine, efficient control for this electric machine there. Without that, if we only do the system level research, it's not going to solve the problem by itself alone. Okay, so that's the main motivation for the research in the electric machine and drive area. And it's expected that by 2040, all new vehicles sales going to be of EV. So which means that at some point that the car makers are not going to make IC driven car at all. It will all be electric vehicles, which translate to millions of electric motors, actually, because each car will have at least one motor. So let's look at the type of electric vehicle that is currently available. Initially, when the concept of EV came, it started with hybrid electric vehicle, or HEV. So what does HEV mean is that you still have the combustion engine or IC engine along with electric motor, which drives the car. And the battery cannot be charged actually by plugging it. It is just charged through the electric machine. The motor or the electric machine actually behaves both as a motor and a generator. So when you are driving the car, it behaves like a motor, but when it is brake, then the engine drives this electric machine as a generator, and it can charge the battery up. A good example or commercialized HEV, quite popular, is Toyota Prius car. And it is actually a pioneer also in the electric motor drive technology for EV. So we will be talking a bit about that motor drive system, what Toyota uses. After hybrid EV or HEV came the plug-in HEV or hybrid electric vehicle, but you can plug in to charge the battery. So only difference was that the battery could be charged from outside. And then last one, which is going to be the future, is the all electric vehicle. So in all electric vehicle, we don't have anymore the combustion engine. The car is driven by the electric motor. And because now engine is not there, obviously motor needs to be more powerful, and battery capacity need to be much larger. So, but remember our car, like especially those who drive car, you know that we have only a limited amount of space in the car to install your motor or battery where the engine is. The car, you don't want a large car. You still want your same car, same comfort, right? But in that, so you have limited space. And in that limited space, you have to fit in this battery and this motor. So what should be the, because the motor is now going to replace the IC. So how is power, or how much power it will need? So to understand that, maybe we can look a little bit deeper into the electric traction drive inside the electric car. So especially those of you who drive car, maybe you can relate to it. Once you press the accelerator, usually your engine will bring the car to a certain speed, minimum speed, that is your first gear. And then if you want to go to a higher speed, you change your gear and then it accelerates further to a higher speed. But in EV, once you do the same pressing of the accelerator pedal, it is going to actually give a command to a controller. That is a speed command. You want to drive the car at a certain speed. And that command from the controller goes to the inverter, and inverter drives the motor at that particular speed. So why would need the inverter? Because your motor going to be a 3-phase AC motor. It cannot be a DC motor, because the main reason it cannot be a DC motor is because a DC motor is inefficient. It is also its power density, that is power per meter cube, is much higher. So if we want to use a DC motor there, it will be a very large motor. And as mentioned previously, we only have a certain amount of space in the car. We don't have infinite space. So we have a volume constraint there. Now, so that means if it's an AC motor and our main energy source is battery or DC, so we need that conversion from DC to AC. So that's why inverter will be an essential part of it. And other things like the other power supply, which we already have, even in our IC driven car, still need to be there, such as that DC supply for auxiliaries, such as your music system in your car, or the light, or the any other electrical component on board. So that those parts still need to come from the battery, but usually they are at a much lower voltage level. So the auxiliary supply could be at 24 volt, whereas the motor or the DC bus or DC voltage that goes to the motor could be as high as 600 volt. So that's why there is a DC-DC converter between the battery and the auxiliary supply. Now you can see that the main power or the main force which will drag your car is the motor now. There's nothing else. The motor needs to be quite powerful. If you think of forget about the passenger car, if you think of a truck, can you imagine how large this power needs to be if you want to drag a truck? So that means that we have, main problem is we have constrained volume, and the other problem is that we need a much powerful motor. So as a solution, some of the EV company actually use 2 motors to drive the front wheel and the back wheel. So this is like a 4-wheel drive. But the smaller ones use only 1 motor. So the most popular electric car commercially available at this stage is Tesla's. I am not sure whether it is available in India or not, but it is quite common nowadays in Australia. Like we see it means out of maybe 100 car, at least 10 car will be Tesla. So it's quite getting very common. So the Tesla EV doesn't have any engine, only driven by electric motors and battery. It's a fully or all electric car. And it solved the problem of the powerful motor by having two motors. Now, of course, a car itself is quite expensive, and then EV is even more expensive. So where the cost relates to or comes from, that's as you have seen previously, the inverter. We will need an inverter if we have to drive the car by battery, DC power. So that inverter cost is about 40%. And then the other one is the obviously electric motor. That's 20%, and all other things like transmission system that's required to mechanically connect the motor to the axle drive of the wheels, and the other smaller power electronics converter, cables, etc. These are the component of a cost component. But you can see that the major cost is power electronics, and the electric machine together forms about 60%. So one goal, that's why for electric machine drive, is to reduce this cost. So one is to reduce the size, because you have constraint on volume, only constraint, you only have a certain amount of size or space in the car. The other one is cost, so that it can be made affordable to everyone. Otherwise, we will still have the same problem. If people are still using IC engine driven car, then it's not the solution for CO2 reduction. When the majority of the world population can have access to EV, only then it will have major effect. So we need high power dense, that means a very small motor, but with a much higher or stronger power. And we need it to be cost effective so that it could become widely available to everyone. And then the third is, of course, it needs to be highly efficient. So based on this, actually a set of specification was determined by US Energy Department. That was in 2016, so some time ago. Part of this specification has already been achieved, although it was supposed to be quite challenging when it was first came out. So one of the major challenge at that time was, of course, to reduce the cost, achieving an efficiency greater than 95%. Then having a voltage not more than 600 volt. This was set as a safety concern because more than 600 volt in a car could be dangerous. So that's why this 600 volt was set up as a maximum limit for the back EMF that can be generated by a motor when it is driving at its highest speed. Okay. And the DC-link voltage set to be about 450 volt, but in recent time, it has actually exceed 450 volt. It's gone to nearly 600 volt itself. And that power, the peak power, and there was a rated power, the two things. So peak power was the power that is required to make the car accelerate to a minimum speed. So again, when That means you are in first gear, and you have to accelerate to at least 20 or 10 km/h speed. And only after that you can change to your second gear. So to go to that first gear speed, you need the highest power and highest torque as well. So that is, and they wanted to achieve it within 18 seconds. Okay, very, very fast acceleration, that means. And but once you have gone to this minimum speed or accelerated up to this minimum speed, after that, if you want to go to a higher speed, let's say from 10 km/h to 40 km/h or 60 km/h, that is your second gear, you do not need anymore as much power actually. The power requirement reduces. It can be 30 kilowatt. So that is actually the behavior of a traction drive. Any traction drive, you need a constant maximum torque initially to go to a minimum speed. And then once you got that speed, after that, your power requirement and torque, actually torque requirement reduces when you go above that speed. So the minimum speed, rotational speed was set in this specification was 2800 RPM. And then maximum speed for the motor was set at 14,000 RPM. So you can see that the ratio between these two speeds is about 5:1. So during this range of speed, actually power need to remain constant because your torque is reducing, your speed is increasing. So torque times speed is power. That's why power can remain constant if you can keep power constant during this time. And that's why this speed range is known as constant power speed range. And wider constant power speed range is one of the desirable characteristics for traction motors. So a lot of research has been done to improve or to achieve a wide CPSR, this constant power speed range. We'll talk about that a bit later again, but the concept of CPSR is that we will now look at why it is important for traction drive. So here you can see the torque versus speed characteristic of in your left-hand side, the traditional torque versus speed characteristic of a car with various gears. As I said, in first gear, you need to have a minimum certain torque. And then as you go to second gear, your torque requirement reduces. And as you change gear, your torque requirement start to reduce. So this is achieved actually in the IC engine by using complicated gear system. Okay, and we all know gear systems are inefficient, and engine doesn't have an ideal traction drive type torque speed characteristic. We force it to behave this way by using those complicated gears. But when we are going to EV, if we can eliminate this gear system and can achieve the ideal torque speed characteristic of a traction drive in the motor itself, this torque speed characteristic, as you can see, the black line, then it will be quite useful. So that was one objective, to achieve a ideal torque speed characteristic in the traction motor. That means having a constant speed range or constant power speed range. So how this power becomes constant, you can look at that simple relation of power versus power speed power, speed, and torque. So if your speed increasing, torque reducing, power should remain constant. So that's the constant power. So ideally, this power of the motor should remain constant when speed increases and torque reduces in traction drive. So what's the use of keeping this power constant can be understood here. We can start with a very simple relation of force is equal to mass time acceleration. You all know, right? So starting from that, force is equal to mass time acceleration. So dv dt is our acceleration, m is mass, and f is force. So from this relation, we can, with a little bit of mathematical manipulation, should be able to find what is the acceleration time of a vehicle to go to a certain minimum speed, PRV, let's say. This minimum speed, 60 mile per hour in this figure, okay? And the minimum speed was about 25 mile per hour. That is the constant torque part to your first gear speed part. So that from here, we can actually also find out what is the power of the motor need to be for a certain amount of mass, certain amount of acceleration time, certain amount of certain value of speed, minimum speed, and certain particular speed at which you want to drive the vehicle. Okay, so this is coming from the basic force equal to mass time acceleration, this relation. As many of you know, force can also be written as power over velocity. Okay, so that's how this power relation was developed. And we can see that immediately the motor power will be function of mass of the vehicle, the acceleration time, inversely related with power, and the square of those velocity. This same equation we can't convert to rotational speed, because as we know, the motor is going to run actually with rotational speed, whereas vehicle, when our car drives, we consider it as the linear speed, that is mile per hour or kilometer per hour. That's our linear speed. But the motor actually, or your wheels actually running in rotational speed. So that's why we are more interested in the rotational speed. So the same equation can be converted now to rotational speed using the simple relation of linear speed is equal to rotational speed times the radius of your wheel. In this case, this R means radius of your wheel times the rotational speed of the motor. And so if we convert our linear speeds in the first equation to the rotational speed, the power equation actually becomes in terms of inertia, J. Okay, so from here we can see that the power will be the rated power of the motor will be function of the inertia. Inertia means how heavy the whole your vehicle going to be. That will determine actually your inertia, your required acceleration time, and the motor speed, the minimum motor speed, and the speed at which you want to drive the car. So in terms of speed of the motor, that minimum speed is usually the rated speed of the motor or the base speed of the motor, whereas the speed at which you want to drive the car is the maximum speed of your motor. So now we define the constant power speed range as the speed ratio between the maximum speed over base speed. Now, coming back to in this equation of our power equation, if we set that we have our base speed is 0, that means our CPSR is going to be infinite, right? Omega b 0 or base speed 0 will mean that our constant power speed range is infinite. If the constant power speed infinite, that will mean that we do not need a minimum constant torque to accelerate our car to a minimum speed. We can accelerate to whatever speed we like from 0 speed. So that's, it would have been torque speed characteristic would have been like as shown here. And if this condition can be achieved, then the power, rated power required by or rated power of the motor will be from this basic equation, half inertia times square of the maximum speed over the acceleration time. On the other hand, if we say that we do not have any CPSR, we do not have any, or rather, if we say that our maximum speed is our rated speed, that means we have only a CPSR equal to 1. That will mean that the motor will always operate with constant torque. Torque will never reduce, okay? So under this condition, if we again use our first fundamental power equation and set omega max as equal to omega b, we will get that the required rated power is twice the power required for when CPSR is infinite. You can check the equation 1.6 and 1.7 yourself. If you compare those two, clearly you can see that power requirement will be 2 times of the when CPSR is infinite. However, in practical case, we cannot ever get a traction drive with infinite CPSR. Okay, we always will need certain amount of constant torque to accelerate it to a minimum speed. So that means if, in other words, we cannot get infinite CPSR, but if we can make the CPSR as high as possible in a motor, we will be able to reduce the required power to achieve the same performance. Okay, that's the main point of having a wide CPSR. The large CPSR will mean that rated power required from the motor can be minimized. Okay, we cannot halve the power, but between half and 1, we can get something, right? If we increase the CPSR, or if we have a large enough CPSR. So that's why, as you can, if you recall, in the previous US specification, the CPSR was set as 5:1. In fact, achieving 5 was quite a task in 2016, but there are now different motors are coming where CPSR could be quite high, close to 5 or even higher than 5. We have developed a few motors where we are able to achieve CPSR as high as 7. Now, with CPSR, it's not only the wide CPSR, but we also need, as I mentioned earlier, the cost. So we have to reduce the system cost of the traction drive. And cost means it is cost of the power electronics as well as cost of the motor. So when you design a motor for traction drive, we want wide CPSR. We want minimum cost. Minimum cost actually translates also to smaller and lighter motor. So reduction of the weight and reduction of the volume. So this is also another 2 objective when you want to design traction motor. So we can say now we have a couple of objectives for traction drive or traction motor. One is it must be highly efficient. It must be cost effective or with minimum cost. We must have wide CPSR. It must be of lightweight. It must be of smaller volume. That is kilowatt per kg and kilowatt per liter must be high enough. So when we optimize motors, this could be our objectives when we design it. So that actually brings to the end of the first section. And it's open for question if you have any question. And we can also take maybe 5 minutes break as well. If you have question, you can use chat window. You can also raise hand and turn on your mic. And those who are in the room, maybe you can use the mic.
As of now, no questions from the offline students.
Any questions?
I think no,
No question?
yeah, no questions from the offline students. No? And even in online, no one has any.
Online, I cannot see any chat. Yes.
Yeah.
Okay. Do you like to take a break for, I don't know, maybe 5 minutes?
Yeah, if you want, you can take 5 minutes break and continue.
Yeah, okay. So you can think about what we have just discussed. It is like you can note down the most important point that you remember from what I have just discussed. And also think about whether there is any point which is not clear to you. So that also, which could become a question. So during these 5 minute breaks, just reflect what we have discussed.
Okay.
So it is this is like 54 in my watch. I don't know what's the time there.
It's 11:38 now.
11:38.
38.
Okay, so that means 11:38. So
11:43 or 44 is right now.
yeah, 11:44 back. Okay.
After 5 minutes, we'll start again.
Okay, can we come back? Can I have your attention back?
Yes, sir.
Still no question?
Any questions for the offline participants? Yeah, I think that as of now, no questions. They may ask at the end of the session.
Okay. All right then, so let's proceed to the next part of the lecture then. So first part, we discuss electric vehicles, traction drive. We need a minimum speed up to which the torque need to be constant. And after that torque drops, the speed ratio between this minimum, this constant torque and the maximum speed to which the vehicle can accelerate, during this time, power can remain constant, which is the CPSR. Wider CPSR means we can have we can use motors with lower power. We also want to reduce the cost of the motor, and we want to make it lighter and smaller size. Now, the next one, the next application is the direct drive renewable energy conversion. Okay, so in this section, we will try to understand how the direct drive technology for renewable energy is evolving. We will look at the advantages of direct drive generations, and then we will also look at what is the desirable performance for an electric generator that can operate with direct drive. So if we look at wind energy conversion as an example for wind renewable energy generation, initially when it was developed, some of you may know it, that it used actually the asynchronous machine or induction machine as the generator. The reason was that because, as you know, when the wind speed changes, the blade of the turbine is going to rotate at different speed. So you could have variable speed at the input shaft of the generator. And synchronous machine usually whatever its speed and its frequency is directly related. So synchronous machine doesn't tolerate change of speed much, whereas induction generator, because it has a slip between the synchronous speed and its actual speed, it can allow variation of speed, or it can tolerate variation of speed. So that was the main reason for using induction generators in the wind energy conversion. And usually traditional induction machines or induction generators runs at a speed of, let's say, a 4-pole induction generator speed will be about 1450 RPM. Whereas a wind turbine rotates at a much slower speed, as could be as low as 50 RPM. So one is at 50 RPM, other one is close to 1500 RPM. So you obviously needed a gearbox. Okay, so between the generator and the turbine shaft, there was a gearbox. But in the recent times, we want to eliminate this gearbox because gearbox is a weak link. It is inefficient. The gearboxes are a mechanical device. It's also its lifespan compared to the generator and the turbine is less. So if your lifespan of the turbine and the generator is, let's say, 20 years or 30 years, a gear need to be replaced every 5 years. So it's a maintenance cost. Okay, so that's why the wind energy industry is moving towards elimination of the gearbox. And other type of renewable energy conversion is the wave or your tidal energy. The wave and tidal energy, as you know, that it moves up and down. So motion is actually linear, not rotational. So in this type of renewable energy conversion, again, previously there was a gearbox and the conversion from linear to rotational speed because your generators are always rotating, not linear. So now the thinking is that why use a rotational machine there? Why not use a linear machine? And why don't we eliminate the gear and the mechanical conversion? So that is for the other type of renewable energy conversion systems, where again, direct drive is becoming more popular, especially in industry. And as you know, the wind or even solar, all are quite intermittent. You could have today a very sunny weather and you have a lot of solar energy available. You might have a very good windy day, or you are getting more than you require the wind energy. But then at night, you don't have solar energy, or in a very still hot day, maybe your wind turbines are not rotating at all. So which means when we try to get energy from renewable systems like wind or solar, since it is intermittent, so the grid usually need kind of a support. So one support is the storage by adding large battery storage along with the grid. So that's one of the solution proposed. And other is that we support the grid by adding additional gas-driven smaller generator systems. So this gas could be hydrogen gas, it could be natural gas. Of course, when you are burning natural gas, you're going to emit CO2. So hydrogen gas generators are being proposed. But this type of generation, because they're going to be large power, but you don't want them to be like large generator system that we have in our current grid system, because developing again those large generator systems is going to be very costly, and it's may not be it may not be, and it's not going to be the main generation anyway, because our main energy source is going to be photovoltaic and wind energy. These are kind of support generators. So why would you like to build the large generators? So you want small ones, portable ones even. So how can you make them small and portable? There are this concept of micro turbine. So this micro turbine based systems actually going to, if you want to use them, they need to, especially if they are gearless system or direct drive system, then they need to run at very high speed so that the whole system becomes portable, small. So in the direct drive applications, we have a couple of things coming up. For wind energy conversion, you want to eliminate the gearbox and run the generator same speed as the speed of your turbine. In the wave or tidal energy space, you want it to be a linear generator rather than rotating one. And in terms of, and the supporting generating system, which are proposed as the microturbine, gas-driven microturbines. Again, if you want to make them direct drive, they need to be run at very high speed. So one side, we need, for wind generation, we need a low speed, because the rotor blades and rotor shaft runs at low speed. So generator, when there's no gear, the generator needs to run at low speed. On the other hand, the microturbine, if you remove the gear, the generator and the gas turbines need to run at a very high speed. And the third one is the linear generator. In this course, we are not going to talk about linear generators or linear machine at all. It could itself be a course, so we will not be talking about it. So we will concentrate mostly on the direct drive wind generator systems, and also the high speed. We'll discuss a little bit about high speed machine design. So when we replace or remove the gear, the advantages are it's going to reduce the complexity. It also going to increase the reliability, efficiency, and lifespan, and reduce maintenance in the direct in case of wind wind energy conversion system, or also same benefit stands for gas microturbines. But the shortcoming is that they are going to be much more expensive than the existing system, because the generators, especially for wind energy conversion, when you need low speed, the generators going to become very large and heavy. So why it can become large and heavy, we can understand again quite easily from here. So rotors of a wind turbine, the speed could be as low as 20 to 100 RPM. wind speed could be 8 meter per second. Okay, for an 8 meter per second, a large wind turbine speed is about 10 to 20 RPM. Previously, you had the gear, so you didn't have to worry about what's the speed of your generator. It could be 1500 RPM, it could be 3000 RPM. But now, if you want to remove the gearbox, then your generator also need to run at same 20 RPM or about 20 to 100 RPM, whatever the rotor shaft speed is. Now, what that means is that you want still certain amount of power out of your generator. Your speed has now reduced. So that means you need a very large torque. Okay. Now, how do you get large torque? The torque comes from the torques which translate to power. So torque and power both for a electric machines relates to the magnetic flux in the machine, the current that you are pushing through, and number of poles, magnetic poles in your machine. So if we we cannot keep increasing current or magnetic flux linkage for a certain volume of a machine. It has limitation. We'll discuss those things when we discuss the design, but we should know that we have limitation. We cannot have infinite current, or neither we can have infinite flux linkage. For a certain power, we have these two it has certain values which we have to keep it at those values. So then how can we increase torque? One option is to increase the pole numbers, okay, magnetic pole numbers. And also for those of you who knows the synchronous speed is frequency of the supply proportional to and inversely proportional to number of magnetic pole in the machine. So we can see if the low speed, that means high pole number from here. And we can also see from the torque equation that high torque can be achieved with high pole numbers. So that means if we want a direct drive wind generator, the number of magnetic pole in the machine going to be much, much larger. We can look at a very simple example here. Let's say we want 50 hertz supply. If our generator runs at 1500 RPM, then the pole numbers going to be, or pole pairs going to be about 2. It's going to be 2, not about. It's going to be 2 if you calculate it, right? This is, if you make it 1500 RPM, convert it to radian per second, F, the frequency 50 hertz. And if you calculate out simply what is pole pairs, you'll find that it's 2. The number is 2. Now change that 1500 to 50 RPM. If we do that, if we change it to 15 RPM, from 1500, if we reduce, let's say by 100 times, it's 15 RPM, 15 RPM, and we still want 50 hertz supply. So immediately you'll see that pole pairs now going to be 200 times more than previously. So before, what was 2 pole pairs, now we will need 200 pole pairs. So we have to fit these many poles in the generator, which means the diameter of the generator going to be very large. It was in a recent research paper, it was shown that if we want a direct drive generator to replace a conventional generator of 1500 RPM, the diameter could be as high as 7 times larger than the conventional generator. So that means we have a very large generator, and we have to, if it's a wind generator system, we have to mount it on the top of the tower. It's heavy, it is large. So you can see a comparison here between a conventional generator with a gear and a direct drive generator, but that use permanent magnet. By using permanent magnet, it actually, because permanent magnet machines has very good power density, this power per liter or power per kg, so they can be made, the weight can be made lower than a conventional geared system. But still you can see the diameter is much larger compared to that conventional one. And also the cost in this table one, the cost is compared for different component. And the second table compares the for a direct drive and gear systems, the mass of the various components. And both cases, cost and mass, both cases you will see that direct drive is large. So now challenge is how to design an efficient generator that is not heavy and not too large for direct drive generator, especially for wind energy. That means low speed, high torque, how to make the generators lighter and smaller, getting the same performance. So that's the challenge for wind energy system. And as I said, for the microturbine based systems, direct drive systems, the speed could be as high as 120,000 RPM. Okay, 120 kilo RPM or 120,000 RPM. So for this type of very high speed, there is another problem. The generators now becomes actually mechanically vulnerable. As the speed increases, the centrifugal force that acts on a rotating body increases. So when the electric machines rotate at very high speed, that centrifugal force operating or it experiencing could be very high and can break the material. The stress it creates on the material could be so high that it exceed the yield strength of the material. If it happens, then the machine will break into pieces. So that means when you design high-speed machines, the mechanical stability, mechanical stress also need to be considered, not just electromagnetics. Okay, in all other designs, the electromagnetic, and of course we have to consider temperature. So thermal and electromagnetic need to be carefully studied when you design it. But when you do high-speed machine design, you also have to consider the mechanical stability or mechanical strength. Okay, so it adds extra challenges when you do high-speed machine. So if we want to summarize the challenges, I divide it into 3 categories. The low speed category, where we have the wind energy conversion, that is the direct drive. And if we look at the industry trend, you will see that most of the time, the direct drive generators that is being proposed or even be commercialized are permanent magnet synchronous generators, not conventional synchronous generators. They are all permanent magnet synchronous generators. They need low speed, but high power and torque. Speed could be a few tens to hundreds of RPM, whereas power could be tens of kilowatt to even megawatt. Okay, up to 10 megawatt direct drive generators has been designed. Then the next one is the medium speed range or medium power range. The application is electric vehicle. The trend here is, again, if we look at the commercialized EV and what type of motor they are using, you will see that it is permanent magnet synchronous motors, especially the interior type. So what is interior type, we'll discuss later, but that's the trend. And in this application, we need a few hundreds to few thousand RPM speed, whereas the power could be tens of kilowatt to hundreds of kilowatts. So it sits in the middle, okay, EV application for motor design. And then comes the high speed, the micro turbine, and also the all electric aircraft has been proposed in recent times, that even in the aircraft or aeroplanes, the engine will be replaced one day by electric motor drives. So, but that's in the future. Currently, I think initially it will be hybrid systems, because we don't have motors yet designed which could give us high power as some megawatts, 2 megawatts or above, but with very lightweight. That's not even been designed yet. So that's why the aerospace, all electric aircraft for commercial aeroplanes not going to happen at least not in the next decade. I think it's maybe will take a couple of decades before we see all electric passenger aircraft, large passenger aircraft. But small ones are already appearing, the 1-seater or 2-seater aircrafts with electric motors. So that is, in those application, again, the motor need to be at very high speed. The region for high speed motor for electric aircraft is that when the motor operating frequency is very high, that means speed is very high, they can be made very small and lighter. You will see one of our design, how we make it how small by just designing it for a very high speed. So that's the region in electric aircraft going for high speed machine. And again, the dominant motor type is permanent magnet synchronous machines. So this application, micro turbine, gas micro turbine, or all electric aircraft, speed is high, but power is relatively medium, we can say, at least at this stage, tens of kilowatt to hundreds of kilowatt. Megawatt is not yet possible. It's possible, but it's not. It will not be. It could not be made as light as we want for this type of applications. So that's why the high-speed motors power rating is at this stage up to hundreds of kilowatt, and each one has their own challenges, as we discussed. For direct drive, wind energy, that means low speed, because it needs high pole numbers, so size is large, heavy. So how to make them smaller size and lighter. For EV, it needs to operate with a wide constant power speed range, which is a challenge especially for permanent magnet machines to have wide constant power speed range. We also want to make it efficient. Obviously, also we want to make it cost effective. And the last one, for the high speed, because of the mechanical stress, we have to consider very carefully the mechanical stability of the motor or generator when you design it for high speed. And also the losses could be very high compared to other motors. As some of you know, the loss in a machine, electric machine or electromagnetic device is the eddy current loss and a hysteresis loss. But the major loss is the eddy current loss. And of course, resistance loss, but the resistance loss is in your wires or windings or in your stators, whereas the eddy current loss happens in all the magnetic materials, okay? And eddy current loss actually increases square of the frequency, and your speed is related to your frequency. So higher speed means high operating frequency. High operating frequency means very high eddy current loss. So that's another added challenge for high-speed machines. Now, we have seen in these applications that permanent magnet machine dominates in all these emerging applications. So why so? They are highly efficient. Why they are highly efficient? Because in a permanent magnet machine, compared to a conventional machine, you have magnets in the rotating part, or magnets could also be in the stationary part, but you have replaced a winding or copper with magnet. And since you have replaced the winding or copper with magnet, so you have reduced the copper loss, okay, or I square R loss. If you have a winding instead of a magnet in the rotor, let's say, then the rotor would have extra copper losses because you have winding in your rotor. Now you're replacing it with a high density permanent magnet, so that loss is gone. So that's why they are highly efficient. Their efficiency is higher compared to all conventional three-phase or single-phase machine. And because they uses high energy density magnets, that's why also they could be made very small compared to conventional motors for same power rating. So if you compare a 1 kilowatt induction motor and a 1 kilowatt PM machine, you will see that PM machines are far more smaller. And third advantage of it is that it gives you much better dynamics performance. So for EV or for all electric aircraft, you want better dynamics. You want to accelerate your car fast. You want to accelerate your, for electric aircraft, you will need certain acceleration, okay? So that dynamics can be much easily achieved in a permanent magnet machine compared to other conventional machines. So these are the three main driving force behind the popularity of PM machine in the emerging applications. Now, what are the different type of permanent magnet machine? Maybe some of you know about brushless DC machine. So brushless DC machine is a kind of permanent magnet machine, but it is a bit different. Many people actually confuses BLDC or brushless DC machine as the permanent magnet machine, but they are different. So we'll discuss this, how they are different, maybe in tomorrow's lecture. In like a broad classification, we can divide PM machine into two categories: radial flux type and axial flux type. So what does radial flux mean? That the magnetic flux that comes out of the magnets crosses the air gap, radially and then goes to the stator to complete the magnetic path. Okay, so those type of machines are known as radial flux machine. Whereas the axial flux, we still have magnets in our rotor, we still have our stator, but the flux, magnetic flux, crosses the air gap in the axial direction of the machine and completes the magnetic path. So that's two types we can divide PM machine into. And then under radial flux, we have the brushless DC machine, which behaves more like a conventional DC machine. Whereas the other one is permanent magnet synchronous machine. So this behaves like a synchronous, conventional synchronous machine. There is a difference, bit of difference between their operating principle as well as their drive systems. So when we discuss this, you will be able to see that difference clearly. And then under PMSM, we can again divide into two types. One is called surface type PMSM, and other one is called interior types PMSM. So what's the surface and interior? Maybe you can see the difference here in these two rotors. So surface means the magnets are glued on the surface of the rotor. That's your rotating body. And these are the piece of magnets. So they are glued to the surface. So that's why the name surface type. Whereas the interior type, the magnets pieces are these ones, okay? These square, rectangles that you can see. So these magnet pieces are buried in the rotor iron. That's your rotor iron, and they are inside the core. So that's the name interior type. Usually the BLDC motors are all surface type, but the PMSM could be surface or interior type. And the axial flux machine, most common ones are surface type rotor it has. But again, in this course, we will not be discussing axial flux machine at all. So it again operates quite differently, and its design principles are also relatively different from a PMSM. So our discussion will be PM machine, radial flux, PMSM, a little bit of BLDC, and both surface and interior type. So that's what the course will cover, okay? You can also see the difference of torque versus speed characteristic between surface type and interior type machine. So the torque characteristic, that blue line, as you can see, is for, that's the constant torque part, right? And then for this particular example case, we have a rated speed of about 3000 RPM. So for a surface type, once the motor reaches its rated speed of about 3000 RPM, the torque fall immediately, okay? And power, as the torque was constant and the speed was increasing, power was increasing. But as soon as the torque fall to zero, power also fall back to zero. So that's the characteristic of a surface type PM machine, or SPM. And you can see that they do not satisfy the traction motor's torque speed requirement. Whereas in an interior type PM machine, or IPM, the torque can be extended, okay? It has a constant torque, and then torque starts to fall with speed. So speed can be extended with reduced torque. And the power remains somewhat constant, okay? Not perfectly constant. You cannot keep power constant perfectly in a practical machine, but kind of constant. Okay, so interior type motors gives you the torque speed characteristic that is needed for a traction drive. That's why the IPM motors dominates in the EV application. Whereas for wind energy conversion or other applications, SPM is equally competitive with IPM. Okay, both can be used, but in traction, the IPM is the more popular choice because it can provide that torque speed characteristic required by a traction motor. So we'll discuss how and why this happens in the tomorrow's lecture. One thing we should also understand is that in the permanent magnet machine, one of its biggest disadvantages is that you cannot change its magnetic flux because the flux is coming from the magnets. We cannot control the flux, okay? Whereas in a conventional DC machine or even a conventional synchronous machine, you could have a field circuit. So field circuit, you can control the field current, and by doing that, you can reduce or increase the magnetic flux that comes from the rotor, okay? Whereas in a permanent magnet, we can't do that. It is magnets. So that's why in first look, it seems like we cannot actually reduce its magnetic flux at all. However, there is a way of doing it. And when we operate a motor above its base speed, and when we want to keep the power constant, in fact, we need to reduce the magnetic flux in the machine so that the back EMF doesn't exceed the rated voltage of the motor, okay? You may remember from your DC machine theory that back EMF or EMF is proportional to speed time magnetic flux. So if your speed increases, and if we do not reduce flux, back EMF E will increase. In DC machine, conventional DC machine, because we have that field winding or field current, we could reduce the flux by reducing the field current. And that's how we can keep the back EMF constant at the rated value, even when we run our DC motor above the base speed or rated speed. But now in permanent magnets, since we don't have that luxury, so how do we get that flux weakened when we want to go above rated speed? It can be done in permanent interior type permanent magnet machine actually by taking help of negative armature reaction. The armature reaction means the magnetic flux that comes from the stator current. Okay, so the magnetic flux produced by the stator current, if it can be produced in the opposite direction of the magnetic flux coming from the rotor, then the resultant flux could be reduced. So that can be done in an interior type PM machine because it has a smaller air gap compared to a surface type machine. And that's why we can extend the speed beyond the base speed with falling torque in an IPM machine. Another advantage is that the interior type machine actually behaves like a salient pole type synchronous machine. Tomorrow we'll look at the difference between salient pole and uniform air gap synchronous machine in a more detail. But for those who remember, the salient pole synchronous machine has a non-uniform air gap. So in one point, the air gap is smaller compared to the other point. So because of that, it actually can provide an additional torque, or it can induce an additional torque known as reluctance torque. So IPM machine actually behaves like a salient pole synchronous machine, and that's why it has that additional reluctance torque, which is again beneficial. We get more torque out of the same size. That's another advantage or another reason for use of IPM machine in traction drive. So that brings us to the end of this part of the lecture. What we can summarize now is that for automotive tractions, we need new efficient machine with wide CPSR. For gearless operation or direct drive wind generator, where the speed is low, you need high torque. And that brings additional challenges. Whereas in case of gearless high speed, low torque operation, it has another set of challenges. So two different type of challenge with the direct drive operation. PM material, they are expensive, the rare earth PM materials. Also, one problem with PM material is that they are like the source of rare earth material is concentrated mostly in China and a bit in also in Australia, but Australia doesn't process actually rare earth material. So most of the rare earth material processing happens at China. And so that's an worry because, as you know, there is this geopolitical issues and conflicts are happening. So there is this problem. People are thinking that, okay, since rare earth materials comes mostly from China, they can, if there is a conflict, they can stop providing that rare earth material to the world. And then what will happen if we have all our motor generators that have PM material and we have no access to PM material, then how the world will come to a halt. So that's a big issue. So that's why how to reduce the dependency of PM material is again a research area, whether you can reduce the amount of magnet material in the motor generators. And also, like countries like Australia and US has started to processing their rare earth materials or mining. They have started mining the rare earth material, but it's going to take years. It's not going to happen overnight. So that supply issue is an issue for the whole world. And then the other problem is that the PM material has a certain temperature capability. It cannot operate with temperature higher than 120 degrees centigrade. So if you are using PM material in the motor or generators, it's cooling. It needs to be cooled very aggressively so that the temperature doesn't exceed ever above 120 degrees. Now, and then high-speed machines, since their frequency is very high, so they need converters with wide bandgap devices. So not just silicon device will work for them. We may need to use new type of device, switching devices such as silicon carbide or GAN devices. So that the developing of converter, high switching frequency converter with wide bandgap device is a research area. And all these motors and generators, they actually require control. Okay, they are not like conventional synchronous or induction machine, which you can just plug into three-phase supply and forget about it. But it's not like, it doesn't work like that in PMSM. You need a converter, even when it is you are supplying it from a three-phase AC, you still need an inverter actually. In EV, obviously, your source is battery, so you need an inverter. But if we use PM machine in industrial applications where the supply is three-phase AC, you will still need a control and inverter. That's how its working principle is. So that's we'll discuss again in the next tomorrow's lecture. So you'll see why without inverter it cannot work. However, that provides us also an advantage that we can control them very precisely. So robust control techniques being developed and being improved nearly every year. We are seeing advantages or the advances in the control techniques. Then these machines also require always a position sensing. So that position sensing is, if we can eliminate that position sensing, known as sensorless operation, that is another research area. So we have done quite a lot of work on sensorless operation. We may discuss a bit about it when we discuss the control techniques of PMSM machine. And then last but not least, the problem with PMSM machine is that because these machines are aggressively designed, so they could have mechanical sensorless, magnetic saturation. Okay, so when they have magnetic saturation, their machine model, which we will discuss again in another lecture later, you will see that the machine model needs certain parameters from the machine. And these parameters can vary if there is magnetic saturation. And if the parameters are uncertain, then those robust control or all this mechanical sensorless control or whatever, all advanced control technique may not perform optimally if we do not know the parameters properly. And then estimating this parameter itself could be also quite a challenge. And how to incorporate this uncertainty, parameter uncertainty in the control is also a good research area for motor drive operations. I think that brings us to the end of today's material. I can see there are some questions, so we'll do some discussion. These are the reference for today. So let's see the question. So question here is for those who are in the room, if you haven't seen the question in the chat window, let me read it. Thank you, Himanshu. It's a very good question. He has learned about reluctance machine. So reluctance machines are, the question is, is the reluctance machine considered better in terms of magnetism and temperature? Kind of, that's in summary, the question. So what is reluctance motor? First, we have to think about it. So if in the rotor, the one that you have seen previously, this, let's say our PMSM rotors that in the previous slides. So here we have magnets. Now imagine there's, especially in this interior type, imagine we have no magnet but the air here instead of magnets, okay? that will become a reluctance motor actually. So when your rotor doesn't have any magnet or any field winding, we get reluctance motor. So yes, reluctance motor in first go looks like could be a very good alternative, but there are problems again with reluctance machine because now we only have torque coming from the reluctance of the motor. So that's why they need very high current. So something similar to, it becomes something similar to induction machine. So their efficiency could be, compared to PM machine, could be lower. But because they don't have magnets, yes, that's why they are not affected by the temperature. So their rotor is quite robust. Mechanically also they are robust, and or could be made robust mechanically. And they also thermally they are robust. But the main issue with reluctance machine is that they are not efficient, their power density is relatively low, and they could be very noisy. Their torque has a lot of, that torque is not smooth. So they, when they rotates with a jerk. So that jerking moments translate to a vibration and noise. They could be noisy. But they are considered as alternative for PM machine, especially if we do not want to rely on rare earth material. And they are also less expensive because you are not using expensive magnet material there. Okay. Is there any other questions? That's a very good question. So I loved it.
Do you have one more question from the offline participant? Is the question clear now? This question from the participant is audible to you now?
I cannot hear.
Yeah, 1 second.
Yes, it's better now.
Can you please tell me what swing is? Like microwave swing is? Can you please comment on that one?
Summary points, sorry. Here, yep.
Can you please comment on the swing grids, no? Like microgrids you showed, like swing grids you showed. Can you please comment on that one?
I can't catch your question. Can you repeat again? It's a little bit blurred, the noise. You can repeat again.
You showed like swing grids, right? Like microgrids, there's swing grids. Can
Yep.
you please comment on that one?
So you're talking about swing grid.
Yes, no, please comment on
And what's the question?
that. Can you tell about that? Like I know about microgrids. Can you please tell about swing grids?
Okay, all right. So you want to know about swing grid. So we have talked about a little about the intermittency of the renewable energy, right? That is you could have if you are using solar energy, or if you are using wind energy, it may not be available, right? Or it can vary rather. Like when you have a very nice cloudy, a very sunny day, you will have certain amount of solar energy, but if you go to a cloudy day, you will have much less, right? So when you have this variation of generated energy, then that means your generated voltage is also varying, right? And if you have a wind generation, when the wind speed changing, your turbine is rotating at different speed or variable speed, and your generator could be also producing voltage of different frequency, right? So when you have a grid in which the voltage and frequency are not fixed, we have swing grid. Okay, like in our conventional grid, we have fixed voltage and fixed frequency. Like in India, we have 50 hertz and 240 volt supply, right? So and a grid operator must maintain certain that frequency. They allow a little bit of variation, 5% plus minus. Similarly, voltage plus minus 5%, but that's all. You are not allowed to change anything else. If you turn off a generator from the grid, your frequency and voltage doesn't change. It's always remain constant at that value. Okay, 240 volt, 50 hertz. Whereas in a swing grid, it can change. Your voltage can change. Your frequency can change. Okay, and that is because you have renewable energy, so you do not have a constant source of voltage and constant source of, or your voltage and speed are changing or frequency is changing. So that's as a support, you could have battery. Like battery can provide when frequency will drop. If you have not enough energy in your grid, right? The load is demanding certain amount of power, but you do not have enough energy to supply because you do not have enough wind to turn your rotor turbine. Okay, so in that case, you will not have enough energy. If you have not enough energy, then the frequency can drop in the grid. Okay, or if you have more energy and you have not enough load, then also your frequency can go up. So then how can we prevent this in the swing grid is by allowing battery or storage. So if you have more energy, you store it in the battery. If you have less energy, you take that energy from the battery and support it. Or you could have like the generators that we talk about, like micro gas turbines or hydrogen generators. So they could be supporting system there as a when you have not enough energy, they will provide that. Or if you have more energy, you store it. Okay.
Thank you.
Any more questions? Yeah, I think, ma'am, no more questions from the participants. So we'll wind up this session here. Yeah, thank you, ma'am, for the interesting and very informative lecture. Hope that participants have got enough information on the topic, EV drives and renewable energy. Thank you all. Ma'am, we'll have one group photo. Hence, I request all the participants to turn on their cameras. Ma'am, could you stop sharing?
Yeah, sure. I'm just trying to stop. Okay, I stopped. Yep.
Now, I request all the participants to turn on your camera. Yeah, thank you all. Thank you, ma'am. Our next session will start at 1:30 p.m. Instead of it's 1 p.m. It will be starting at 1:30 p.m. This will be purely online session. Hence, I request all the participants from inside and outside NIT are requested to join online through Zoom platform. Thank you.
Thank you. So see you tomorrow morning, and maybe I can join a little bit in the afternoon session. Is it? Can I talk to
Yeah, it's not
Lalit? Yeah, okay. Do you want me to join as well a little bit in the beginning?
Hello, madam.
Lalit, do you want me to join in the afternoon session for in the beginning, or you will be able to manage it?
If you can manage your time, you join, otherwise I can just go. I can do it.
Okay, so I'll leave it to you then, and I have provided you the quiz link, so please do share that at the end of the lecture, the quiz, so that we can tomorrow then we can discuss on about the quiz results with everyone.
Okay, I got it. As I said before, 15 minutes before the end of the session, second session, I think
Yeah.
They will submit within 10 minutes. Okay.
Yeah, it will not, it's very simple, and do not stress at all about the quiz. They are very simple ones, and you should all be able to do it. It's just to refreshing our knowledge about electromagnetism. Okay, see you tomorrow morning, and we'll start the actual PMSM machine. Okay, thank you so much for everyone, and hope to see you again tomorrow. Bye for now.
Thank you, ma'am. Thank you all the participants. We meet again at 1:30 p.m. online.